Okay, let f of x equal the square root of x on an interval 4 to 9. Show that f of x satisfies the hypothesis of the mean value theorem. F of x is the square root of x. The hypothesis for the mean value theorem says that the function needs to be differentiable on the open interval, continuous on the closed interval. But our interval is from 4 to 9. So, continuous on 4, 9, there's nothing that would make that discontinuous. Differentiable on 4, 9, that's smooth. There's nothing that would make that so that you couldn't take the derivative. So it satisfies the hypothesis of the mean value theorem. Now we have to find a number c that satisfies the conclusion of the mean value theorem. The mean value theorem concludes to say, well, if that's true, continuity and differentiability, then there's some place c, there is a c in the interval AB that when you take the derivative and plug that c in, you get the same as f of b minus f of a all over b minus a. I'm sorry, 9 minus 4. Yeah, sorry. Let me go ahead and put the b and the a in there first. F of b minus f of a over b minus a. So identify a is 4, b is 9, f of 9 is the square root of 9, f of 4 is the square root of 4. And so we have that f prime of c equals 3 minus 2 over 9 minus 4, or 1/5. We have to find the c. That makes this true. So we go to the function f of x and we take the derivative. If f of x is the square root of x, think about it as x to the half, its derivative is 1/2 x to the negative 1/2. Or better said as 1 over 2 square roots of x. So, we then have 1 over 2 square roots of x needs to be set equal to that 1/5, and it's up for us to solve for x. If you want to call it c, you can. The first thing you would think of would be to cross multiply. And so we have that 5 is equal to 2 root x. 5 halves is equal to root x. Or that x is 25 over 4. And that should be one of your choices. 25 over 4? Yeah. X is 25 over 4. This is your answer. Okay, great. Use the tangent line approximation to y equals the square root of x at x equals 16 to estimate the square root of 17. Here's what's going on here. We have the same square root of x function. And we have this known value that when x is 16, the square root of x is 4. And so what we want to do is move to a nearby x value, use the tangent line to approximate the function. So at that point of tangency, there's a tangent line. Just exaggerated here. And what we're going to do is move to the point that is 1 away. Move to 17. And plug, essentially, 17 into the tangent line equation. If you go and find a tangent line equation and plug 17 in, it'll be a pretty close approximation to the actual square root of 17. We have a generic version of the tangent line equation. Looks like f prime at a times the quantity x minus a plus the function at a. What you have to do is identify that a is 16, f of a is 4, and x is 17. And just plug these numbers in. We have that y equals f prime of 16 times 17 minus 16 plus f of 16. And this will give us the number that is the approximation to the square root of 17. But it comes from the tangent line. And what we find out is that we need these two numbers. We know what f of 16 is, 4. We know what 17 minus 16 is, 1. But that gets multiplied by f prime at 16. F of x, once again, is the square root of x. Its derivative is 1 over 2 square roots of x. How do we get that? We just treat x to the half power, bring down the half, take it to the negative 1/2. So then what is f prime at 16? 1 over 2 square roots of 16, which is 1 over 8. And that gets multiplied by 1 to give us 4 1/8. Since the answers are in mixed number versions, we can say that that is our approximation. We don't say equals, it's approximately equal to that. So that's our approximation, 4 1/8. And we need a calculator to see how good of an approximation it is. But we're done. Okay, so we have to find the local minimum value of the function f of x is 4x cubed minus 15x squared plus 12x plus 8. The local minimum value. We learned that we need to study the first derivative. Nice thing about this is a polynomial. We get 12x squared minus 30x plus 12. And we need to search for where your derivative is 0 or your derivative is undefined. These will give you critical numbers. And these are your possibilities for places where you can attain your local max or your local min. And what we find out is that since f prime is a polynomial, then it'll be defined everywhere. So we can skip that part of it and focus only on f prime equals 0. So we set it equal to 0, and the numbers are too large for us to factor as it is without having a lot of trouble, so we can factor out what they have in common. Taking out the 6, we'll be left with 2x squared minus 5x plus 2 equals to 0. And that factors as 2x and x, 2 and 1. The signs are the same. They're both negative. So minus and minus. Alright, so this is your first derivative. And we set it equal to 0. It's either going to be where 2x minus 1 is 0, or where x minus 2 is 0. So we have our two values, x equals a half, and x equals 2. Go to the number line, place those 0 critical numbers, or place all critical numbers on the number line. Analyze the signs of the first derivative. Plug into the first derivative. If you pick test values, you pick a test value of 0, test value of 1, test value of, I don't know, 10 or 3 or 4, whatever you want. What are you plugging into? Plug into the factored form. 2x minus 1 and x minus 2. And so, if we plug a 0 in, 2x minus 1 is negative, and x minus 2 is negative. The product is positive. If we plug a 1 in, 2x minus 1 is positive, but x minus 2 is negative, so we get a negative. And if we plug a 4 in, they are both positive, so we get positive. How do you get a local minimum? When you change from decreasing to increasing. Your local min is going to occur there. That doesn't tell you what your local minimum is, local minimum value, but it tells you that it occurs there. It occurs at x equals 2. If we wanted local max, it would occur at x equals a half. Okay? Now we take and find the y value, local minimum value of the function. So we take f of 2. And we get 4 times 2 cubed minus 15 times 2 squared plus 12 times 2 plus 8. 4 times 8 minus 15 times 4 plus 24 plus 8. 32 minus 60 plus 32. 64 minus 60, or 4. That is f of 2. That is your local minimum value. Find the slope of the tangent line to this curve at the point 2, 1. First thing you notice about the curve is that the x's and y's are so intertangled that you don't have y explicitly defined for x. You don't have y equals some f of x. What you have is y defined implicitly with x, and so we have to use implicit differentiation. Take the derivative of each term, focusing on the terms that have both x and y in them. Those terms with x and y in them will require a product rule. The terms without the x and the y, we can just take the derivative as normal. We'll have 16x cubed from the derivative of 4x fourth. Now what we do with 8x squared times y squared, we treat 8x squared as the first function and y squared as the second function, and we use the product rule. We say derivative of the first, 16x, times the second, plus the first, 8x squared, times the derivative of the second, 2y, but remember, dy dx. So this is first derivative times the second plus the first times the derivative of the second. But then it happens again with the next term. Take it as a minus 25 x squared y. Treat the whole minus 25 as the first function, y as the second function. So we'll get a minus 50x times y minus 25x squared times dy dx. Once again, first prime, derivative first times the second, and then we have the first times the derivative of the second. Alright, great. Now we're on to the last term, 4y to the fourth, which has 16y cubed, but dy dx for the chain rule, and then derivative of 0 is 0. Let's focus on all the terms that have dy dx in them. 1, 2, 3 of them. The terms that don't have dy dx, we're going to shift them over to the other side. By subtracting them or adding them, whatever sign you have, just do the opposite sign. And then these guys that still have the y prime, the dy dx, we can factor out the dy dx from these. So we'll do two steps at once, and hopefully not make a mistake. We could plug in now. It's your choice whether you want to be a plug in now or a plug in later person. Let's do a plug in now. We have what is before we start moving, what is 16? X is equal to 2. X is 2 and y is 1. Okay, so 16 times 2 cubed, 16 times 2 times 1 squared. Put this 8 and this 2 together and call it 16 times 2 squared dy dx minus 50 times 2 times 1 minus 25 times 2 squared times dy dx plus 16 times 1 cubed dy dx equals to 0. So we'll be a plug in now, where we have 16 times 8 128, 16 times 2 32, 16 times 4 is 64, minus 100, 25 times 4 minus 100 dy dx plus 16 dy dx equals to 0. And then once again, these guys here that don't have a dy dx, we shift them over to the other side, but let's put them together. We have a 128 plus a 32, that's a 160, minus 100, 160 minus 100 is a 60. And then what's our dy dx's? We have 64 minus 100 plus a 16. Grand total of 80 minus 100, or negative 20, equals to 0. So what we're looking at is 60 minus 20 dy dx equals to 0. So 60 is equal to 20 dy dx, or dy dx is equal to 3. Okay, so we'll take G as the answer. We have a hot air balloon rising straight up from a level field. It's tracked by a rangefinder. This here is called the rangefinder. And the balloon's launching point is right there. rangefinder is 600 feet from the liftoff point. And so we just write on this triangle right here. That's going to be a constant, 600 feet. This is the launching or liftoff point. Making a right triangle. 600 is constant. And what's changing is the distance the rangefinder is from the balloon and the height the balloon is off of the ground, off away from the liftoff point. Also, what's changing is the angle that the rangefinder is using, the angle of elevation. We'll call it theta. Okay. This question does not ask anything about the distance the balloon is from the rangefinder, like some of the questions do. So this might not play a role for us. So we could actually ignore it and focus only on our changing picture, 600, right triangle, theta, and y. Then we have a snapshot picture where we're worried about, at the moment, the rangefinder's angle of elevation is pi over 6. So theta, at that moment, theta is pi over 6. This is still 600, and we have to figure out what y equals. Okay, opposite the pi over 6 is 30, and think of a special right triangle where we have the 30, the 60, and the 90. Opposite the 30 is x, opposite the 60 is, the hypotenuse is twice x, and opposite the 60 is x root 3. Special right triangle, the SAT. And so we can use that. Opposite to 30 we have essentially our x, and that's what we need. We call it y here though. Opposite to 60 is 600, so what we have is x root 3 is equal to 600, and so x is 600 over root 3. We could just use trig. We don't have to do this special right triangle. We could just use trig and say that the tangent of pi over 6 is y over 600. So y equals 600 times the tangent of pi over 6. We definitely could do that. But not too many people can like rattle off the top of the head what the tangent of pi over 6 is. But what you can do instead though is think about it as sine over cosine. The sine of pi over 6 over the cosine of pi over 6, and then that will be something you can just read off your cheat sheet. It was 600, and the sine of pi over 6 is a half, and the cosine of pi over 6 is root 3 over 2. And so you get the same thing because you get that y is the 600, and you take the half and you multiply by 2 over root 3. So you get the same thing, 600 over root 3, but this is more efficient. You get there faster. Okay, so that's what x is, and we'll call it y here. 600 over root 3. Let's leave it like that for now. 600 over root 3. And that's our snapshot. Go back to the changing picture and set up your equation that relates your variables, and we already have it that the tangent of theta is y over 600. I don't like fractions, so I'm going to multiply by 600 like I did before. 600 times the tangent of theta is equal to y. and we're ready to take the derivative. 600 secant squared theta, but d theta dt is equal to dy dt. So y doesn't play a role here. Actually, all that time we spent finding out what y was, we end up not even using it, unfortunately. Theta is pi over 6, so we need the secant squared on pi over 6. D theta dt is 0.2 radians per minute. We'll trade that in for 0.2 is a fifth. 0.2 is 2 over 10, which is a fifth. Okay, so this is a fifth, and secant squared on pi over 6 is what we need. We don't know secant squares, but we know cosines. Secant has a relationship that it's 1 over cosine, so secant of pi over 6 squared is 1 over the cosine of pi over 6 squared. Cosine of pi over 6 we've already seen is root 3 over 2. So take root 3 over 2, square it, and then take its reciprocal. We get 3/4 is root 3 over 2 squared, and take its reciprocal. So all that is to get 4/3 as the secant squared on pi over 6. And then we're almost done. We're just going to plug in now. This is 4/3. And so we're looking at 600 times 4 over 3 times 1 over 5. Okay. And the 3 can turn the 600 into a 200. And the 5 could turn the 200 into a 40? Yeah. So the answer would be 160, sorry. 40 times 4. 160 feet per second. Feet per second would be the answer. So you have the position of the particle moving along a straight line given by that equation, and we're asked to find the position of the particle first when it's at rest, and determine the total distance traveled, secondly, during the first 5 seconds. So it's S of t is 2t cubed minus 15t squared plus 24t. When the particle is at rest, that means when the velocity is 0. Velocity is s prime of t, so take s prime of t and we're going to set it equal to 0. We get 6t squared minus 30t plus 24, and we're going to set this equal to 0. Factor out the 6 to make it easier to factor. We get t squared minus 5t plus 4 equals 0. So either the way the polynomial factors, either t is 1 or t is 4. Those are the 2 places when the particle is at rest. 2 times when the particle is at rest. They don't want the times though, they want to know the position of the particle. If we plug a 1 in, we get 2 minus 15 plus 24, 26 minus 15, we get 11. S of 4 is 2 times 4 cubed minus 15 times 4 squared plus 24 times 4. It's going to take a little bit more work. 4 cubed is 64. If you double 64, you get 128. 4 squared is 16. And 15 times 16 is 240. 24 times 4 is 96. You put the 96 together with the 128, and you get 224. And take away the 40, and you get a negative 16. So those are the two positions when the particle is at rest. That answers the question for A. We have 11 and negative 16. The question for B, however, requires more work. We have to now go and find the total distance traveled during the first 5 seconds. With the aid of a number line, at time t equals at position 0, we're there when t is 0. For the first second, we travel to t position 11 at t equals 1. I'm sorry, t equals 1. Now the particle's at rest. And what happens is it turns back around, and by the time t equals 4, I mean we're at negative 16 when t equals 4. And then it's going to turn back around, and we want to know over the first 5 seconds, so we need to know what happens when t is 5. It's going to take a bit of work though. 2 times 5 cubed minus 15 times 5 squared, and then 24 times 5. Okay, 5 cubed is 125, and when you double it, you get 250. 5 squared is 25. If you take 15 times 25, you get 15 quarters is a quarter short of $4. You get $3.75. And then 24 times 5 is 120. So that you put these two together to give you 370, but take away the 375, you'll still end up at a negative 5. Okay. You just break it into parts. From 0 to 1, the distance traveled is 11. From 1 to 4, however, you go backwards 11 to get to 0, and then another 16 to go to negative 16. 11 plus 16 is 27. That's 11 to get to here, and then 16 more to get to here. A total of 27. And then finally, we have from negative 16 to negative 11. You travel a distance of from t equals 4 to t equals 5. you've traveled back to being forwards again. Forwards a distance of 11 for a grand total of 22 plus 27, or 49 units with the distance traveled. The answer to B. The answer to A would be these two. And then the answer to B is the 49. Okay, the key is the very first sentence. It says the graph of f prime is given below. Not the graph of f, but the graph of f prime. And so, what we need to study for knowing where the function is increasing, that corresponds to where the derivative is positive. But if you're looking at the graph of the derivative, how do you know where it's positive at? And that corresponds to where the graph of f prime is above the x-axis. Actually, what we can do, let's do a number line where we have the points marked off: x0, x1, x2, x3, x4, and x5. And it's a number line with the signs of f prime. And so, between 0 and 1, f prime is negative, is positive, in between x1 and technically through x4. x4 it's 0. Let's just put a little 0 here, and at x1 it's 0 there. But it continues to be positive after that. And so if you ask where it's increasing at, technically we have to say x1 up to x4, x4 up to x5, the union of those is not increasing at x4, so we report it like that. Okay, now when they ask about where the function has a local min, we can go back to the previous and see that we change from f prime being below to above. We change, f prime is negative and all of a sudden it's positive. That corresponds to a local min. And so we can go back to this next question and say we have a local min at x1, but for a local max it never occurs. For a local max we need to change from increasing to decreasing, and that doesn't happen. So we'll say none for that, or not at all, or does not exist, or not apply, or something like that. Great. That's about the first derivative. We jump to asking questions about concavity. But this is the concavity of your function f. So you want to know concavity on f. You know it's directly related to signs on f double prime but your issue is that you are looking at the graph of f prime, and you're interested in, you want to be able to find the signs on f double prime, so you can answer this question. With the same connection that f has with f prime is a connection f prime has with f double prime. If you want to know the signs on the derivative of the graph of your function, you focus on the slopes of the tangent line. And so, if your tangent line slopes are positive, that means that your derivative is positive. And so, if we draw a number line again, the second derivative is positive all the way up to x2, because we have positive sloping tangent lines. It's 0 at x2 all the way through to x4. We have negative sloping tangent lines. Is at x4 where the slope of the tangent line is 0 at, and then between x4 and x5 we have positive sloping tangent lines. So these are the signs on f double prime, and that can help us get the concavity. We say that we are concave down between x2 and x4. You can say that we are concave up from x0 to x2, and then it picks back up again from x4 to x5. Technically union symbol in between. Okay, great. And this will tell us about the next question as well. This will tell us about where we have inflection points. Yeah, let's see. We have inflection points where you change concavity at. So we're going to change concavity at x2 and x4. So the answer to D, the very last question, will be inflection points at x2 and x4. My software is failing on me, so I'm going to go ahead and end this PowerPoint presentation. It isn't working. And then end the recording. Okay, we have this function f of x that we can't find the inverse for, but we're asked to find the inverse's derivative at 7. We go to the formula, which says the inverse's derivative at 7 is 1 over the derivative at the inverse of 7. We have to find the x value that gives a y value of 7. We can't solve it algebraically, we have to use guess and check. So we set f equal to 7. X cubed plus 2x plus 4 equals 7. Let's put some wrong guesses in there. At 0, we get 4. That's not 7. At 2, we get 16. That's not 7. At -1, we get 1. That's not 7. At x equals 1, we get 1 plus 2 plus 4, which is 7. Okay, good. So 1, the answer to this question is 1. So then that takes the place of the inside. And so now f inverse prime of 7 is 1 over f prime of 1. If f of x is x cubed plus 2x plus 4, then f prime of x is 3x squared plus 2. F prime of 1 is 5. And so our answer to the question is 1 over 5. Alright, what we notice is that we have a function x raised to another function 3x. And so, replacing f of x with y, we have to get the 3x out of there in the exponent. It can't stay up there. So when you have a function raised to a function, we're going to use logarithmic differentiation. So that means we take the natural log of both sides, with the purpose being that it allows us to bring down the exponent. The 3x that's up in the exponent comes down in front and multiplies using the property of logs. The second step is to take the derivative using implicit differentiation. So we get 1 over y, but that has to be multiplied by dy dx. That's equal to, now we have to use the product rule here, treating 3x as the first function and ln x as the second function. Derivative of the first times the second plus the first times the derivative of the second, which is 1 over x. The x's cancel, and we get 3 log x plus 3. The third step is to basically solve for dy dx, multiply by y, but at the same time we do that. After we're done with that, replace y by the function of x, the original function of x. Okay, so we go and say that dy dx is y times 3 log x plus 3. Replace the y with x to the 3x. And that is what the derivative is. We're particularly interested in the derivative at a third. We're going to plug it in. 1/3 to the 3 times 1/3, 3 log 1/3 plus 3. And we get 1/3 to the 1, and we get our 3 log 3 plus a 3, and then finally just distribute across, because the 3's are going to cancel out, and you get the answer of, I'm sorry, that's a log of 1/3 there we go. We get the answer of the log of 1/3 plus 1. And that corresponds to letter E, the log of 1/3 plus 1 is the same as 1 plus the log of 1/3. Okay, now we have the function y equals x squared times e to the negative x and we want to know about the local min and local max. Take the derivative using the product rule, where we consider the x squared the first and the e to minus x the second. Derivative of the first times the second plus the first times the derivative of the second. Anytime you have e to any function, you repeat that back as its derivative, but the chain rule says you're not done there, you need to multiply by the derivative of that exponent. So that is our first times the derivative of our second. If we're interested where it's positive and negative at, we want to set it equal to 0. If you're going to find local min and local max, it's either going to occur where the derivative is 0 or the derivative doesn't exist. These are our possible candidates. And it turns out that it's neither the f prime undefined doesn't apply, so the setting equal to 0 does. We factor out what they have in common, leaving us with a 2x. Oh, I'm sorry, we could have taken out an x. Leaving us with 2 minus x. There's your derivative in its factored form, and you want to know where it's equal to 0, so you set it equal to 0 and treat it as if it's 3 different terms, not 2. Treat the x and the e x separately, and we're interested in where this is equal to 0, either x is 0. It turns out that e to the negative x is never 0, and 2 minus x being 0 means that x is 2. So we have those 2 points to worry about, 0 and 2. We should study the first derivative and see how the sign changes. Now you're going to plug into the derivative, but the factored form of the derivative. You're going to plug into x e to the negative x times 2 minus x. On top of e to the negative x never being 0, it's also true that it's always positive. So when it comes time to figure out about sign changes, it's not going to come from that part. You can focus on the x and the 2 minus x. Get your test values. And check the signs. If you have a negative 3, you'll have a negative times a positive, this thing being negative and this thing being positive, so it'll be a negative. If you have a 1, positive and positive, so it switches. And if you have a 2, if you test something bigger than 2, you'll get a positive and a negative. So it goes back to being negative. You have a local minimum at 0 and a local maximum at 2. But that's not the value. That's just the x value where they occur at. You plug in 0 and 2 to get the y value. You get 0 squared e to the 0, which is 0. And at 2, you get 2 squared e to the negative 2, 4 e to the negative 2, or 4 over e squared. The local minimum, they told us to call lowercase m. The local maximum, they told us to call capital M. And it's our job to subtract capital M from lowercase m, and we just end up with 4e squared because the lowercase m is necessarily a 0. So 4 over e squared would be the answer.